Gauss law is a very powerful tool to find the electric field. If you have a enclosed charge, certain charge inside certain surface, then you can find the electric field anywhere outside or on the surface of that enclosed surface. Okay, so first thing we have to know is electric flux. So let's talk about electric flux. The meaning of flux is anything that is flowing. So electric flux means we will be talking about electric field lines. So we know the positive charge. From the positive charge, electric field lines are going out. They will be perpendicular to the surface and pointing outwards. If here is negative charge, electric field lines will go inward, right? Like this. So to define electric flux, let's see few examples here. If there is zero net charge inside the box, let us take an example of a box. We can take any example, any surface. It could be sphere, or it could be any other shape, cylinder, or any other shape, or irregular shape. For instance, let's take a this type of box. If inside this box, let's say uh, there is no charge, okay, what will happen then? Of course, if there is no charge, there is no chance to have electric field, right? Net electric field E equal to 0, because we don't have any charge. There is no chance to get out electric field lines from this box, or electric field lines also cannot enter into it, okay, because there is no charge. There should be negative charge to enter the electric field lines in this box, and there should be positive charge to initiate the electric field lines, so that electric field lines go out from this box. Okay, let us see the another case in which there is net charge. Remember, the net charge is important. Okay, here you can see net charge. Okay, so in this case, net charge is 0. However, we have charge inside. Net charge in this box is 0. That means here is let's say this is plus q. Let us suppose this is just one proton and this is one electron, right? In electron and a proton, the charge is same, positive and negative, which is electronic charge 1.6 into 10 to the power negative 19 coulomb. Same thing for this is negative, and for proton 1.6 into 10 to the power 19 coulomb, right? So they will cancel each other, and this box is electrically neutral. So net charge inside the box is 0. Okay, in this case also, there is no net outwards or inwards flow of electric field, that we call electric flux. Okay, if there is net flux, so this is the box I just wrote like rough, and here is plus q charge here. Right now, here is the net charge, right? Because of this net charge, electric field lines will go out from here in this way. Okay, so right now this surface will have a net electric flux, net electric flux, because there is net charge. Okay, so similarly, if you put negative charge in this box, what will happen? There will be electric flux, of course, but direction is opposite. Okay, so this is called electric flux. So first thing we have to understand Gauss law is electric flux. Okay, so it is denoted by pi e, which is electric flux, and it depends on electric field E and area of this surface, right? Whatever the surface structure, it could be sphere or it could be something like irregular shape, something else. We have to know that surface. Okay, let's see here how to calculate electric flux. To calculate the electric flux, let us set up equation how we can calculate electric flux. Let us see here, these are electric field lines, red arrowhead with arrowhead. These are pointing towards, let's say this is positive x-axis, right? And we have this surface which is perpendicular to these electric field lines. Let us draw uh, a perpendicular vector which is vector A, let's say, which is perpendicular to this surface, right? So if you look at the angle between this vector which is perpendicular to this surface and these electric field lines, what is the angle between? Angle is 0, right? Because this vector and electric field lines are parallel to each other, and angle between E and A is 0. Let's say if it is angle is phi, it is 0. Okay, so in this case electric flux, which is denoted by pi e, it's right here, will be equal to E dot A. This is the scalar product, right? We have two kind of product, vector product and scalar product. So if it is scalar product, E A cos of phi, which is equal to E A cos 0. Cos 0 means what? 1, right? Which is E A. Directly multiplying electric field with area, surface area of this object gives you the electric flux, right? Electric flux, that is simply flow of electric field lines through the surface, gives you electric flux. Okay, so this is the one case, right? And at which theta is 0 or angle, this phi is 0. Okay, phi may not be 0, that's why we have another case. Let us see this one. In this case we have tilted this surface like this. If you draw a perpendicular line from its surface, perpendicular making 90 degree over here, this vector is making certain angle with electric field lines, right, which is pi. So in this case we don't have option to put cos pi equal to 1, right, because it will give you certain other value. So your pi e will be again scalar product of E and A. This is the surface area of this structure, and E is electric field lines, right? Electric field strength. So E A cos pi. So in this case, if angle is other than 90 or 0, you can write down this one. This is the common. Okay, this is page on tilted from a page on condition orientation. Okay, let's see some other configurations, which is this configuration. Right now the vector A, which is the perpendicular line drawn passing through this surface, right, and electric field lines are going in this direction. The angle between these two, that is vector A and electric field lines, is 90. So that's why using this equation over here, E dot A is equal to EA cos 90 degree, which is equal to EA cos 90 is 0, right? So you will get uh, 0, which is phi e. So in this case, pi e is 0. Electric flux is 0. Okay, so uh, we have formula then, pi e. The common formula to calculate the electric flux is E a cos phi. So remember, this pi is angle between E and A. Okay. Okay. So we can write down now electric flux in these formats. There are different formats. Flux of non-uniform electric field. Okay. If electric field is uniform, we can directly write down, like, if electric field is uniform, it will be something like pi e is equal to E will be constant and integration of dA will be A, right? If electric field is non-uniform, it is not constant throughout the area, then you can write down this way. Okay, so pi e equal to integration of E cos dA. We already know this relationship, right? We are just using this integration because we have non-uniform electric field. This is non-uniform. Okay, this is non-uniform, and E perpendicular here is E cos of phi, right? And it can be expressed in terms of E dot dA, because E dot dA, E dot A or dA, right, small surface element, is equal to E cos of phi dA. This is simply the scalar product. Okay, so this is the way how you can calculate um, electric flux. Now let's define Gauss law. So Gauss law states that the total electric flux through a closed surface is equal to the electric charge inside the surface divided by epsilon naught. That is, the total electric flux phi is equal to Q enclosed, that is total charge enclosed, right? For example, this is the surface, and what is the charge inside? If charge is not there, what will be the electric flux? That will be 0, right? Divided by epsilon naught. So this is the quite simple rule and a very important rule, because from there you can calculate the electric field strength. Okay, so this is Gauss law. So this directly relates, look at here, uh, this is actually E dot dA, right, which is equal to Q enclosed divided by epsilon naught, right? Look at here, right here is electric field and this is the charge. So Gauss law connects electric field with the charge enclosed. If certain charge is enclosed inside a surface, this surface is said to be Gaussian surface. This is just imaginary surface. There is no surface like this around any charge, but you can imagine the surface around that charge. Its shape might be spherical or some symmetrical. If it is symmetrical, it is easier to calculate, right? If it is not symmetrical, it will be very difficult to deal with. So this is Gauss law. So this one, right? Pi e, electric flux through a closed surface. So this symbol right here indicates the closed surface, right? Right here, charge Q is here. Okay, uh, plus Q. It could be negative Q also. Anything will work. Then electric flux through a closed surface of area A, area of this whole thing, right? Area, if it is a sphere, area will be 4 pi r square, right? If it is r. Surface integral of E, surface integral of E, this electric field, this is said to be surface integral because we have taken area here, so this is surface integral, right? This is equal to Q enclosed, the total charge, let's say capital Q, right? Total charge enclosed in the surface divided by electric constant. You know epsilon naught is electric constant. Its value is 8.854 into 10 to the power negative 12 Newton meter square per coulomb square, right? So this is the constant. So we can express Gauss law in various form, right? We already know these kind of equations, which is actually expressing flux in different ways. E cos phi dA, E perpendicular dA, E perpendicular is actually this one, right? And in vector form, E dot dA is equal to Q enclosed divided by epsilon naught. Okay, let's apply this Gauss law to find some uh, electric fields. For example, this is electric field of conducting sphere. So this sphere is conducting, okay, and it has charge q. Look at here, charge q is here, and the radius of this one, this is the radius of this sphere, and let's draw a Gaussian surface, which is actually the another concentric circle around this sphere, and the radius is r, right? This is the radius here, this length, radius of this sphere is r. So your goal is to find the electric field it on this surface, which is Gaussian surface, right? This one, this one, this one, this one. Let's say if it is positive, right? The charge here is positive q, positive q. Then electric field lines will be like this. These electric field lines will point outwards. That we call positive electric field. Okay. Okay. Let's calculate and get it. So we know, look at here, these electric field lines, if you draw a vector perpendicular to the surface, that vector A will be this one, right? Which is perpendicular to the surface. So these are electric field lines and this is a vector. What is the angle between them? Angle is 0, right? Because these lines are parallel. Right here, when they just start, they are parallel. So if they are parallel, the phi is 0. That means if you start from here, phi electric field is equal to E cos phi dA, right? So uh, E and cos phi are constant. You can take it out. Cos phi, then dA. So cos phi is 1, right? Because cos of 0 gives you 1. So what is integration of dA? It gives you A, right? So since this is a sphere, area here is the area of this Gaussian surface. This is Gaussian surface, Gaussian surface. uh, Area of this Gaussian surface is 4 pi r squared, right? This is the area of this sphere. So according to Gauss law, this is equal to Q, total charge is enclosed here, divided by epsilon naught, right? If you simplify this one, you will get E equal to Q. These let me put somewhere here. let me write down here. Okay, so E is equal to Q divided by 4 pi epsilon naught, 4 pi here, epsilon naught here, and r square. It is interesting, right? See here, we can get same equation by using Coulomb's law. We already get it, right? So in other way, you can write down E equal to KQ divided by r square, right? Where what is K? K is 1 divided by 4 pi epsilon naught. Okay, so this is electric field strength on this Gaussian surface because of this charge right here, Q, the conducting sphere, right? In case of conducting sphere, remember the charge will be located on the surface. It will not be distributed uniformly inside. It will be located on the surface. This is one case. To find the electric field of point charge, you can apply same approach. This is charge Q, which is point charge. Radius of this Gaussian surface is r, and our goal is to find E, right? As like before, I'm not redoing same thing again. The electric flux phi E will be EA, right? Electric field strength multiplied by surface area of the sphere of Gaussian surface. And again, what is the area of a sphere? 4 pi r square. According to Gauss law, this will be equal to charge enclosed divided by electric constant, right? From there, again, E will be equal to Q 4 pi epsilon naught r square. This is electric field. Okay, and you can also write down this one in this form, Q square. Okay, so let's check few other shapes. We are just checking few symmetric shapes. This is electric field of conducting sphere. Okay, uh, sphere of uniform charge, that is difference, right? In the previous case, that was the conducting sphere, and right now this is different than the previous one because the charge is uniformly distributed, isn't it? In the conducting sphere, charge is just distributed on the surface. Inside the sphere, there is no charge, zero charge, right? But right now, charge is distributed all over this sphere uniformly. Okay, so if there will be two cases. Number one, if r is greater than r, this r, right? This r, the radius of this Gaussian surface is greater than radius of this sphere, the condition will be exactly same like the conducting sphere because whole charge is enclosed here, enclosed by this Gaussian surface, right? This is Gaussian surface, this one. Okay, so in that case, we can directly write down electric field is 4 pi epsilon naught r square. But if r is less than r, what can we do? If r is less than r, what can we do? We need something else. Let me make a small sphere. This is a sphere right now, and r is this one, not this one now. Okay, so this is the Gaussian surface. Right now, r, this r, this r, right? This is smaller than capital R, this r, this length. You can clearly see from this figure. how can you calculate electric field? It will be different because charge is uniformly distributed. Charge will be, some charge remains outside, right? So our goal is just to find the charge inside. That's all. That's all. So let us say charge density. Uh, Charge density of this sphere is sigma. Okay, this is charge density. Charge density. Now, our goal is to find a charge inside this one. You have to subtract a charge outside. To get that, let's say charge enclosed is something like q dash. The inside, the charge inside this Gaussian surface, inside this one, is q dash, and overall charge of this sphere is q, right? That was q, that we know. If that's the case, then to find a q, if you know the q dash, the volume of the sphere will be 4 by 3 pi r cube. If you multiply this volume by density, the small r, right? Small r cube density, you will get total charge. Similarly, to get the total charge, this q also will be equal to 4 by 3 pi capital R cube into density, because this is volume of the whole sphere multiplied by density. This charge will be equal to this one. So to find the relationship between this q dash and the q, that I mean to express this charge inside this Gaussian surface, the smaller Gaussian surface, right? In terms of q, that is the total charge, I can just divide here by q, and the other side also 4 by 3 pi capital R cube sigma, right? Because charge density is the same inside and outside. If that is the case, you can cancel these things, and these constants will be cancelled, and q dash will be equal to q r cube divided by capital R cube. Okay, now your goal is to find phi. Phi is ea, and area is 4 pi r square, which is equal to q dash divided by epsilon naught, right? That is simply Gauss law. But our q dash is something different. Look at here, q r cube divided by epsilon naught is already here, and the capital R cube. Okay, so let me erase all these things and write down here. So electric field strength E will be equal to q r cube. So these all things will go down. 4 pi epsilon naught r square r cube. R square and r will be cancelled, and E will be q r divided by 4 pi epsilon naught r cube, right? This is electric field when r is less than r. Okay, so let us see some other configuration like electric field of line charge. If there is a line charge like this one, look at here, right? The charge is like line, one dimensional. The let us say length is L, right? So what will be the charge if charge per unit length, that you can say the charge density, linear charge density is lambda. What is lambda? Lambda is linear charge density. Right? what will be the total charge enclosed by this is Gaussian surface, right? Is it should be like cylinder, of course, cylindrical. This is Gaussian surface. The electric field lines will be coming out, it's like a cylinder, and electric field lines will be perpendicular to this cylindrical surface on all sides. Okay, this way, this way. Okay, so if you draw perpendicular to this surface, this will be this one, so pi will be 0 here also, right? Pi will be 0. So you can write down, first to calculate q. Q will be lambda L, because this is the charge density multiplied by length give you the total charge, right? So our goal is 2.5, which is EA. What is the area of this curved surface, right? Not this surface and this surface. Electric field lines are not passing through these two surfaces. Electric field lines are just passing through these surfaces, right? So uh, this will be equal to Q divided by epsilon naught. This surface area of this curved surface of a cylinder is equal to 2 pi r L. The r is the radius, right? Radius of this cylinder, and the length is L. Length is L. So this is the area is equal to Q divided by epsilon naught. From there, you'll get E equal to Q. Now you can convert a Q into lambda L. So I can write down like lambda L divided by 2 pi r L epsilon naught. L and L will be cancelled, and you will be ended off with this formula. Okay, E equal to lambda 2 pi r. R is the distance from this linear charge distribution to the Gaussian surface, right? Actually, that is the uh, radius of cylindrical Gaussian surface. Okay. Okay. So if there is a cylindrical charge distribution, the formula will be exactly same, right? Why? Because if charge is distributed in this kind of cylinder, right? This kind of cylinder, another Gaussian surface will also be cylinder, right? And it will be same case, and you will be ended off with this formula. Okay, field of an infinite plane sheet of charge. This is infinite plane sheet, right? It's like a or paper, right? Regular paper. If charge is distributed in two dimension, like in paper, like this, then Gaussian surface can be drawn like this one, or if I make it like horizontal, something horizontal like this, it will be something here and down there, here, right? So uh, electric field lines will go up or down, right? These two surfaces are important. So if surface of this side is A and other side is also A, so total surface is 2A, right? So that I can write down pi equal to E2A. Based on the structure, it could be sphere, I mean this kind of circle or rectangle or square, any kind of shape could be this. So let's say just A, area is A, because there are two areas having same value, right? Area A over here and area A other side, it will be 2A, which is equal to charge Q divided by epsilon naught. If charge density of this sheet is sigma and area is A, then you can write down like area of this side, right? This much of this sheet will be A, then Q will be equal to sigma A. So from here, E equal to sigma A divided by 2A epsilon. A and A will be cancelled and equal to sigma divided by 2 epsilon naught. So this is the formula for infinite plane sheet of the charge.